participating in Texas Instruments Innovation Challenge 2015.
Project is FMCW radar for automotive imaging.
The aim of this project is to provide driver assistance using a radar during low visibility conditions. The reason why we are doing this project is because India is one of the most challenging roads, and most of the accidents are caused due to low visibility conditions, which could have been easily avoided. So we are providing a low-cost radar solution to the masses, which now is only currently available to the high-end supercars. The project is a radar which is mounted on the car. The radar is mounted on a stepper motor which continuously scans to provide maximum aperture. We expect a maximum of 50 meters range in all conditions, fog or rain.
We have three subsystems: the radar front end, the analog front end, and signal processing subsystem. We have a auxiliary onboard diagnostic subsystem which reads real-time car parameters. We have antennas as our antennas. The transmitting antenna transmits S-band signal which impinges on an object and is reflected back to the receiving antenna. Both the signals are mixed at the microwave stage and is processed at the analog subsystem. We have also developed a low-cost system which costs less than 1,000 rupees.
The microwave intermediate frequency signals are passed to the analog front end. We have developed a prototype solution for this earlier. Here is the product solution. The analog front end board comprises of OPA 1612 audio amplifiers, which form a 6th order low pass filter. The gain of the filters is controlled by the TPL 0501 digital potentiometer, which is controlled by the SPI interface. The analog front end board also comprises of TAC 8830 digital to analog converters, which provides the necessary ramp signals for chirp modulation of the microwave components. Here we have the power supply unit. This is our prototype solution. Here's our product. The PSU is mainly formed by the TPS 5430 buck converter. It is capable of supplying +5, -5 and 12 volts. Here we have the stepper motor driver.
We've chosen the DRV8834 bipolar stepper motor driver since controlling a stepper motor is as simple as pulsing 2 pins. DRV8834 has undervoltage, overcurrent and temperature protection.
5430 step-down buck converter to regulate unregulated car voltages. The TPS 5430 offers a simple solution with just 2 resistors, 2 capacitors and 1 inductor. TPS 5430 also offers us thermal protection and over-voltage protection. We use the LM2662 switch capacitor voltage inverter to provide us -5 volts for the op-amps. In total, the power supply unit gives us +5, -5 and +12 volts. From the microwave front end reaches the analog front end board through the SMA connector. The analog front end board consists of TI's OPA 1612 audio op-amps, which are ultra low noise and ultra low distortion op-amps. We control the gain of these op-amps with the TPL 0501 digital potentiometer, which is controlled by the SPI interface from a TIIC series MCU. We also use the DAC 8830 to provide ramp and chirp inputs to the microwave block. The filtered out output is given out from the audio output port.
Now we'll be demonstrating to you the 6th order anti-aliasing low pass filter at a cutoff frequency of 15 kHz, which is the frequency corresponding to the maximum target velocity. Now we see the frequency response. As you can see, there is an attenuation beyond 15 kHz at a steep roll-off rate of -120 dB per decade.
Frequency of the VCO sweeps according to the ramp chirp generated by the TI DAC DAC 8830 with a reconstruction filter used to remove the carrier to produce pure analog output. DAC 8830 is controlled by TIIC series program with Energia. You can observe the frequencies peep in the spectrum analyzer. The peak of the VCO output moves from 2.3 to 2.6 GHz and the bandwidth is 300 MHz.
The experimental setup of Doppler effect with microwave components. The apparatus consists of the microwave block, the power supply unit, the analog front end board and the TIIC series. The microwave block consists of a voltage control oscillator, an attenuator, two low noise amplifiers, a splitter and a mixer. The analog front-end board provides the fixed DC bias level for Doppler experiment. The DAC 8830 is controlled by the TIIC series through energy interface. We have the antennas which transmit and receive the signal. This is the antenna. You can see the antenna feed. As the person with an obstacle moves towards the antennas, there is a change in amplitude and frequency. With a greater relative velocity, the frequency of the beat signal increases, and with the decrease in position, the amplitude swing is higher.
Here is the testing of microstrip PCBs which we designed and fabricated. Our testing has a microwave signal generator, our component, a detector and a VSWR meter. Let us first test the splitter from mini circuits. The input from the signal generator is minus 31 dB in this case. We expect 3 dB down, that is minus 34 dB, but we are getting minus 35 dB as you can observe in the VSWR meter here. Now let us test the splitter. The input is minus 33 dB. We expect minus 36 dB, but we are getting minus 38 dB due to FR4 losses.
In spite of having the components and the PCBs, we couldn't assemble the microstrip board and the OBD due to the high cost involved in reflow soldering. However, we plan to accomplish this in further stages of the product development. Here the antennas are mounted on top of the car. We maximize the antenna aperture by stepping it with a stepper motor, which is controlled by DRV8834 stepper motor driver. We record the reflected signal at each step and further process it to obtain distance information.
This is the demonstration of a radar system on a test vehicle. In this test vehicle, we have a complete prototype solution comprising of mechanically scanned antenna, radar front end, analog front end and DSP mounted on top. We demonstrate a ranging experiment where the cars will approach each other and the car with a radar system will perceive the oncoming car as an obstacle. The recorded data is processed on the DSP and plotted on a CPU. Image shows the range time plot of the ranging experiment. This focused part correlates to the oncoming car. The discontinuity in the plot is due to the stepper scan, as it becomes maximum when the object is in its aperture.